classes using open source hardware flows at Berkeley. Got a lot of interesting stuff to learn about here.
All right, thanks, Jonathan. So yeah, I'm Jerry. I'm a fourth-year PhD student at Berkeley, and in this talk, I'm going to be going over the experience of teaching or TAing and trying to run this course at Berkeley on teaching undergraduate students how to tape out a chip, and doing this all in a single semester, using as many of these open source systems, which you'll hear about or you've already heard about from other Berkeley students today. So I want to provide some background on this course. This course has been around for many years at this point. About 5 years ago, it started with a very small group, a single faculty, very small team of like fewer than 10 senior undergrads, early grad students. And the focus of the course was on more on analog design, analog heavy chips. The course produces, or they try to produce a very single small chip with one or two very skilled TAs. But since then, with the growth of the hardware community and more interest in building custom chips, the course has expanded. We're getting more and more students interested in taking this course. And so last year in spring 2022, we started the course, and we turned out we had like 70 students try to enroll in the course. Eventually, this came down to about 40 or so, mostly junior or senior undergrads. We had 5 TAs. I was one of them. And at this point, the course had really evolved to try to take advantage of much of the work we've been doing at Berkeley to provide or build up these open source flows for chip design and tape out. So using things like Chipyard and Hammer, which you've heard about or will hear about, and trying to tape out these chips on multiple large chips on an advanced technology process, and also include bring up and testing of the chip as part of the course, right? We want to encourage the students to build chips and to actually think about how they're going to bring them up and how they're going to test them when they come back from the foundry. So the organization of this course last year, this was 3 faculty, 5 graduate student TAs, and 40 or so students, most of which were undergrads, a healthy mix of juniors and seniors in the course, and a mix of backgrounds as well. Many of these students, the only hardware course they've taken prior to this class was, I guess, like the intro to, the first year intro to computer architectures course, and the introduction to digital design course, right? So, very limited experience, especially if they're just a junior in the course. The course was offered as a 4-unit class where, according to the university, 1 unit is 3 hours of lab, studio, etc. work per week. This is kind of not really accurate at all, but it was advertised as like a normal class that's kind of project heavy, and you get to build a chip at the end of it. And officially, the course time consisted of 2 1.5 or 2 90-minute lecture blocks per week. And later, you'll see what actually happened when we actually ran the course. So the objective of this course, why are we offering this course? What do we want the students to come out of this course learning? It's intended to be kind of a practical follow-up to the Intro to Design, Intro to Digital Design, Intro to Analog Design courses at Berkeley, so 151, 140. So in those courses, you kind of push a simple toy design through the tools, like a 3-stage RISC-V core, and just get on an FPGA, or do like a fake tape out in ASAP, a tape-in ASAP 7, essentially. But in this course, we wanted to actually push the students through the entire flow, the entire process of collectively coming together, designing an SoC, taping it out, and getting it working in a advanced process node. So with the number of students we had, with the interest in the course, we decided to turn this into taping out 2 chips in 15 weeks. Right, so the requirements for the chips were not that high. They should be somewhat interesting. I'll discuss the bar for that later. And of course, the chips should work, right? We shouldn't, we should expect to bring them back and have later students test them. And as part of that, part of the course is also about producing detailed documentation and specifications for chips. So it's not just doing the work, but understanding what the students are doing, or having the students understand what they're doing well enough, such that they can produce documentation, specification on it, so that later when the chips come back, another student could follow the specification, follow documentation, and understand what was happening, and facilitate the bring up of the chip. So anti-objective of this course is kind of, we don't really want students to design a ton of new blocks, to write a bunch of new RTL, or to reinvent things which already exist in the open source community. So in prior iterations of this course, we've integrated various like open source blocks. I think in spring 21, they integrated like an open source cryptography block and taped that out as part of their chip. So yeah, definitely wanted to encourage students to pull from the open source community as much as possible when they're trying to design these chips. So the timeline of this course, this was a 15-week course. This was the amount of time we had in a semester. So planning started at week -2, where TAs, we all got together and met with the faculty and kind of just scoped out what was going to happen, right? Like, what are the deadlines? When are the PDKs going to arrive? What tools are we going to use? What kind of chips are we going to have the students build? And so when we get to week 0, which is technically even before the start of the semester, we actually got all the students who had enrolled at this point, tried to get them all into a meeting, into a single room, and basically made them aware of what this course would entail, right? The expectations of this course are kind of unlike other project-driven courses where the students can't really slack off here, right? Like, you have to worry about NDAs. They have to know how to use like our research cluster infrastructure. There's going to be a lot of learning to do and a lot of independent problem solving as part of the course. And we basically said that you can't really take this course and try it out for like half a semester and then drop out if you decide it's not for you, right? If you think you might not want to pursue this, let us know, and definitely you don't want to drop out later in the course and then suddenly dump a bunch of work on another student in the course. So at the end of week 0, most of the students stayed on. We still had 40, 45 students in the course. In the first 4 weeks, we were trying to basically ramp up the students, right? Tutorials using many of the open source projects like Shipyard, Hammer, and also running some tutorials on Innovus and Virtuoso just to learn how the tools work, while the faculty were giving high-level lectures on kind of like the more abstract process of going through a tape-out. Weeks 5 and 6, we had kind of 2 weeks to harden the specification of the SoCs, right? So what is the floor plan going to be? What is the architecture going to be? What blocks are you going to integrate? What blocks are you going to design? We threw a bunch of ideas at the students for like random accelerators, random blocks. Basically saw what do they want to do? What kind of devices are they interested in building? And at the end of this, we did a design review with our industry partners, just so the students could see that like what they're doing is actually similar to what commercial industry tapeouts look like. And then you'll notice that we only allocated like 3 or so weeks to design, and this was deliberate. The course is we needed to get them moving through the process. Even at this point, we're like extremely far behind how a tape-out schedule should actually be, right? So in 3 weeks, you have 3 weeks to write all the RTL you want to do, to integrate all the blocks you want to do, and try to get everything as close to clean as possible. And then the last few weeks of the course was basically only integration and testing, no more new features. If you find a bug in something you integrated or built, you can push that in, but 0 features or performance tuning at this point. So going into a little bit more detail, the first 4 weeks of the class on labs, these were primarily using the open source projects we've built at Berkeley, Shipyard and Hammer. I say 95% open source because we were using like a commercial PDK, and obviously that can't be open sourced. But a lot of this material is available on the internet at this point, and we try to publish it after the course. These labs are very guided. You don't really need someone to tell you how to do these labs. You just kind of follow the instructions. It tells you step by step what commands to run, what each command is doing, what output should be coming out. And then it asks you to basically interpret the results. We kind of graded the students on this as well. Can they describe in their own words what is happening in each step of the flow? And part of the purpose of these labs, in addition to just learning how the flow works, is to provide students an opportunity to evaluate like how much they actually want to do this, right? If you have a student who is sitting there, typing these commands in this terminal and is just really hating the process of like debugging errors in make files and Python scripts and Bash scripts, it's not going to be a great time for them, basically. Yeah, we heavily discourage dropping out late in the course. So on week 5, we had 40 students at this point who all had some level of understanding of how the entire process worked, and we needed to organize this into a system where they could actually come together and build something productive. So we had 40 students, 2 chips, so naturally 20 students per chip. we sent out a survey to the students, basically asking them for their preference and their background, skills they're interested in, what have they done before, what internships they've had. And we attempted to assign students to teams by both their preference and background, right? And finally, to maintain the diversity on the teams. We didn't want to have like one team. We wanted to have a range of like juniors, seniors, and an expertise level on each team, just so the students can learn from each other. And so there isn't one team that ends up doing all the work, basically. And this ends up being 5 teams per chip, 4 students per team. On each chip, there was basically a top-level integration team, which was kind of responsible for the top-level floor plan and kind of managing the other teams, kind of. And then there was a bring-up testing team, which was in charge of making sure that everything that everyone else built and integrated could be testable at the end, basically coming up with a test plan for the chip. And the block teams were responsible for actually building or integrating some new accelerator or device or something. And finally, there were 5 TAs, and so we all kind of assigned ourselves to these teams to kind of manage them along the way. So this ended up being 2 TAs per team. So team responsibilities, right? The top-level integration team, they're responsible for the SoC architecture, the top-level floor plan, IOs, pad frame, clock integration. So a lot of the work of integration went to here. Testing bring-up teams kind of worked with everyone else to make sure everything was testable, develop the bring-up plan, make sure that whatever SoC architecture or clocking architecture ended up being integrated, that they had a methodology for bringing it up and testing it. And finally, the block design teams basically had to produce DRC, LVS, and timing clean blocks that the top-level team would integrate and communicate any requirements for integration and testing to the other 2 teams. The structure of this course, there were basically 2 kind of more formal slots for the students. There were weekly team check-ins, which were 1 hour per week per team. Each hour usually 1 hour to 2 hours it ended up being. Both the TAs for the team met with all the students in a room, and we basically just went over progress since last week, any questions they had, any blockers they ran into, basically synchronize and make sure everyone was making forwards progress. Your TAs were providing suggestions on what they should try to do for the next week, and also come up with a plan for the next group check-in or class update. And the class update, since we had 2 80-minute slots per week, we assigned 1 to each chip. And in 80 minutes, we told each team, you have 10 minutes to present updates and slides. Try to focus your updates on what is most relevant to other teams for integrating everything together. And then afterwards, there were like 30 or so minutes to get feedback from professors, TAs, other students. Sometimes a team would suggest something, and the other team would be like, no, we can't really do that, or that introduces a lot of problems for us. Maybe you could not do that. It works like that. Grading for this course was very interesting. It was very project-based naturally, and I guess more add to the challenge. The student experience in this course varied very greatly based on your role, like whether you're doing design, testing, integration, physical design, or digital design. It really affected what kind of work you were contributing to the class. So the grading system we came up with was basically most of the course was graded on, did you actually work on something each week? And it didn't really matter too much exactly what you were doing, as long as it was something that actively contributed to the progress of the chip. So did you work on something? And I guess the other part of it is, did you present on work you worked on to the others, right? So we graded them on kind of like how much they had to say in the various update presentations. And the other 30% were the introductory labs, which you just needed everyone to get through. And finally, documentation, right? So as part of the class, we basically had all the students collectively come together and make edits to one giant design document. At the end of the course, every student had to be able to point to a couple lines in the design doc and say, this is what I did, this is what I contributed to, or this is what I helped a lot on. And this ended up being rather long per chip. So before I go into like a retrospective of how this class ran, some results from this course, per chip, we produced 1,000 lines of new RTL, 500 lines of random test code, and about 100 or so pages of design doc. So using the open source tools Chipyard and Hammer, we have 50 or so lines of chip config, which is just how the standard Chipyard configurations work. And also the Hammer YAML and Hammer hooks, which describe how the VLSI flow progresses. And the result is 1 DRC or LVS clean GDS at the end. So now the retrospective, like what went well, what went wrong, what could we improve upon in this class? So first, the good. One thing which we kind of accidentally stumbled into this. It turns out the way the research clusters are set up is that no one actually has private directories on those machines, which is actually really good because then the students and the TAs could just look in everyone else's repos and see what they're doing. If someone ran into an error, instead of like having a back and forth about it that is going through that communication process and delaying the progress, the TA could just look into the repo and see, okay, this is your log file. You should look at that file and report what's going on and make sure everything is working. The second point is we ran the class on Slack. So this encouraged like rapid on-demand discussion and updates. But we also stumbled into this as well, is that the free Slack is ephemeral. So your messages will disappear after, after a certain time. But this is actually good for the course because it encouraged students. We basically used it to encourage students to not keep all the answers on the Slack, to actually write documentation somewhere else on what they were doing, on how to fix all the problems they encountered. And so I think we're actually going to like keep using the free Slack in the future, even though we might be able to switch to the paid Slack. Of course, we used Shipyard and Hammer for the actual VLSI part of this course. With Shipyard, it was great because the students started with a known working baseline design. And the process of the course was basically, all right, here's the base Shipyard, create a fork for the class, and all the work that is kind of class-specific lives on the fork. So whatever you're integrating, whatever you're implementing, you just submit that as PRs into this fork. And eventually, a couple students actually took responsibility for actually reviewing other people's PRs and just making sure that everything, we wouldn't have merge conflicts and everything kind of merged in and kept the thing working. And finally, because it's all open source, oftentimes the students were able to just refer to like the available documentation online, or even find answers to problems they were running into in the mailing list for Shipyard and Hammer. For Hammer specifically, having this hierarchical VLSI flow support allowed the students to kind of break off and build their own blocks independently, and made it very easy for us to just integrate all those blocks together at the top level, because Hammer just managed all of that for us. And finally, this grade by specification system, where we basically graded them on how much specification they produced, actually worked really well. And I think the quality of the documentation they produced is actually, some of it is so good that we actually want to open source it back into Shipyard. And we're trying to work with some of those students to kind of like upstream their class project into the main Shipyard because it's pretty good documentation. And finally, I guess this is kind of like a principle we try to stick to through running this course, is that the chip should be the minimum viable novelty to be interesting, right? They're not trying to reinvent anything. They're not trying to build the next greatest accelerator. Just what is the smallest thing that you can build that is still interesting enough that you want to go and push it through and tape it out. All right, so what did we kind of fight against in this course when running it? I think the first thing is overzealous RTL development. So a lot of students come out of like the Intro to Digital Design course, they learn Verilog, maybe they learn Chisel, and they're like, oh my God, I can suddenly build anything I want. And that's great. You should definitely do that. But we need to tape out a chip here. And we have to spend some time on physical design. We can only write so much RTL before the testing or the integration becomes too much of a headache. So this is, at every step we had to be like, okay, you gotta stop writing RTL. You gotta think about integration, testing, and we had to fight against this throughout the course. Systems infrastructure, right? We thought we had pretty beefy clusters, but it turns out when you have 30 to 40 undergrads all typing, run synthesis or run place and route into the terminal at the same time, it will crash your machines. So we had to buy new machines. We got a lot of complaints because the student work was like, it was making the machine slow down for the actual research projects that was going on. And this was kind of, we're working on improving this as well. I guess the part on the right is kind of something which, as you in the community must know, it's kind of just an unfortunate part of this area, is that you need a very high degree of Unix literacy in order to be comfortable working with the tools, or the tools assume a very high degree of Unix literacy. Right, so for a lot of the students in the course, this was the first time they had to use a LSF cluster, manage Git submodules, problem solve tool errors that could span across like 3 or 4 different languages in the same command. Basically like collaborate effectively on like one giant project instead of like a small team project. So we did run a couple sessions on like how to use LSF, how to use Git, how to submit PRs effectively in Shipyard. But I think the students which had the best experience in the course were those that were already very comfortable working in like these kinds of environments. All right, so finally, what are the things which I think is kind of unfortunate about running this course? This team-based approach we pursued, it was good for being able to build a large chip, but I think we really wanted the students to come out of this course understanding the entire flow from start to finish. But unfortunately, when they're working in teams, they ended up specializing in one area, and so some of the students did get the full picture view, but I think there's some improvements that could be made here towards just making the big picture more clear to everyone. The second point is kind of related to that. In any course, naturally, you can have a distribution of how invested the students are in the course and how much work they're putting in. And so there really were, a handful of star students that did a lot of the heavy lifting in a lot of the critical areas. There was a concentration of expertise among those students that we tried to encourage them to fan out and distribute to their classmates. There were definitely a few students where you can imagine that if they didn't do the work they did, it's hard to imagine how the chip would have progressed, right? It's hard to think of who else could have been able to do that. And of course, the TA workload is very high. We were basically debugging everything in the process 1 week ahead of the students. And maybe the students weren't aware of this, but oftentimes we figured out the answer a night or two before they asked the question about it, and then we typed the response like we knew it all along. But finally, as you know, the whole tape-out, bring-up, tape-out flow is can't really fit that in 15 weeks. So many of the students graduated before the chips came back. But some of the students who did stick around, particularly the juniors, or the ones sticking around for a master's, when the chips did come back in the fall, they stuck around because at this point they were very invested in seeing the thing work. So they stuck around and basically volunteered to bring up the chip and test it. And it works, and it was great. And finally, this is kind of, we really like to teach this course with a fully open source flow, but the reality is we do need to prepare students for industry as well. And we need to use, I think the situation is getting better, but at the time, we really needed to use commercial CAD tools with a commercial process just so they could get the experience of running those tools and those flows. So this is the last slide. Moving forwards, how is this course going to progress going into the future? It's still being run. It's being run this semester, right now, actually. There's probably some students working on the course as we speak. So I think part of the course is to bring up more guided labs that will try to open source. So these labs will take students all the way from synthesis, placing around DRC LVS, and use an open source PDK like Sky 130, for example, and using open source tools like OpenRoad. And so we want students to be able to see more of the whole picture before moving into the team-based section of the course. The second point is scaling the class. I think we joke about the Moore's law of tape-out class chips is that the number of chips keeps growing every semester, which is somewhat concerning. But it's great. The interest keeps growing. The students really love to contribute to the class. I think the key to having the really scalable courses, which Berkeley has, where there's 2,000 students in the course, which we'll hopefully never get to, is is to have undergrad TAs, right? The course should teach enough information so that the students come out of the course and they come back. The best students can come back the next semester and TA the course for the next generation. And I don't think we're quite there yet, but this is something which is some bright future ahead for us. And finally, we're working on adding more bring up and testing to the class, have the students bring up the last year's chip as part of the class, learn from prior mistakes. And I guess following the model of prior Berkeley courses, there's some effort towards open sourcing as many of the components as possible, making the course materials available online, as I said, switching the labs to use open source tools, and just making it possible for other universities to maybe not run the class, but have graduate students kind of follow the tutorials and basically understand the flow here. So all right, that's my talk. Thanks everyone. I'm happy to take any questions now.
So I have a quick question, Jerry. I'm wondering, so in week 0, you had to have the students sign an NDA.
Yeah.
Were there any procedural issues with requiring that students sign an NDA to take a class at Berkeley? And I'm wondering if in future you could form a double track and basically do both the open source thing and the commercial thing so students could choose their own path. Right.
I think there were issues, but thankfully the faculty pushed most of those through for us. We didn't really have to deal too many with them as TAs, but yeah, I definitely remember there were a couple of discussions about some of the the awkwardness of having a class behind an NDA at Berkeley. But yeah, but I think we also did end up having some special, unusual agreement with the commercial partners, so that this could work and they would be happy with having all of these students sign the NDA without any effort.
Yeah, great talk. So you mentioned that you had a large variance in like student experience before coming into the course, and I was wondering, like what ways do you think you could correct that in the future, or I don't know, mitigate for that? Like, do you think you maybe adding more preparation in previous courses, or have you thought about that?
Yeah, I think that is one of the problems, is that there is like a huge gap that inevitably ends up happening between like learning theoretically about how these flows work and what happens when you actually step into them, right? So the Intro to Digital Design course, where you like do a tape-in, it ends up not being a very good preparation because you don't actually go through a lot of the process of like understanding deep down what the tools are actually doing and what the commands actually mean. I think Nairi was talking about yesterday how we're trying to improve that flow by like taking more of the like real flow steps, like using Hammer and using like the real tools, the real PDKs, and having students use those in the intro courses as well. But I think also like having a variance in background isn't necessarily a bad thing. Like having the students in teams where there were diverse backgrounds meant that they could learn from each other, and I think that was a good part of the course for many of them.
Yeah, definitely. One quick question: was all the RTL in Chisel?
I don't think that's been true for all iterations of the course, but I think in last year's iteration, all the RTL was in Chisel.
Okay. Yeah. Is some of it like in Verilog and System Verilog?
Yeah. I think some of in past years, I believe people have built System Verilog blocks, and sometimes when they integrate an external block, they write like System Verilog wrappers. I think some like the PLL integration, there needs to be like System Verilog stuff around it, so that ends up being like that.
All right. Well, we're going to move along on to our next talk. Stay on schedule, but let's give Jerry another round of applause. Thanks very much, guys.